Hello and welcome for these videos on probabilities. This time we're going to calculate probabilities, and this is the third video of the chapter. Let's go back to the two first parts. The first one was on sets, reminders on sets. We learned how to use the language of sets and their properties. The second one was on calculation of combinatorics. And then we are able to calculate probabilities. Before calculating them, let's define some situations and vocabulary. So first, you've got to know what is a random experiment and what is an event inside a random experiment outcome. A random experiment can be simple or more or less simple. A simple one, roll a die and note its result. So it's simple to think about. A second one could be a little bit more complicated. Organize a race and in the end note the podium. So why not a race opposing 8 opponents here? So to know the podium, you have to know how to try to forecast the 3 first people who arrive in the end of the course, of course. So in the end of the race, sorry. So the first one, the second, and the third. This is 2 examples of experiments. Now you got to know what is the sample space. We already defined it. This is the space, so the set of all the possible results of your experiment. The first one with your die is very simple. This is the set 1, 2, 3, 4, 5, 6. But on the right, what are the possible outcomes of the experiment race between 8 opponents? So let's name the opponents A, B, C, D, E, F, G, H. And then one possible podium could be C, F, B. So omega, your sample space, contains one element, at least, which is CFB. But of course, it could contain the podium BEA, the podium EGH or DBC, and so on. And your goal is to be able to calculate the number of elements of omega without being obliged to write them all. This is our main goal here, and we use combinatorics to calculate this kind of stuff. So the elements of omega are named outcomes. So that are results that come out, a random experiment. So the outcomes on the left are very simple. They are single elements. The outcomes on the right are groups of 3 elements. So that's not as simple. Now, inside all of that, let's define events. Events are something that could occur. And something that could occur is not always a single outcome. It could be some group of outcomes, considering some criterion that you are interested in. So let's take the simple example of the die. And let's define the event A, get an even number. So omega contains 1, 2, 3, 4, 5, 6. And your event contains some outcomes inside omega. 2, 4, 6. So you can say that A is a part of omega and you can name it by the mean of a set. A is actually a set in our language. The event get at least 3 contains the element 3, 4, 5, 6. So it's another subset of omega. And the event get at maximum 2 is the subset 1, 2. So each time you have to define an event, it will fall into a subset of omega. Or it could be an impossible event, so the empty set, or omega itself. It depends on the definition of your event. So since we saw that an event is a set, we can apply on events or what we can do with sets: intersections, unions, and complement. So for example, A inter B means A and B. So you want the elements that are even and at least 3. Which means here 4 and 6. Okay, so if you want to be even and then to be at least 3, you've got 4 and 6. If you want to be at least 3 and then even, there is still 4 and 6. Okay, A into B equals 4, 6. The union is defined by the word or. You want to be inside A or B to create a union B. So you want all the numbers that are even or at least 3. So that means even or 3, or at least 3, okay, or both, of course. So you have to group A and B inside a global set that is named A union B. So at this point, we've got to define the complement of a set. So we already defined it, but it will be named a contrary event with a bar, okay? A bar at the bottom of the letter, at the top, sorry. We have to be placed in an ideal situation. That means omega is a certain event and the empty set is an impossible event. Why had it to be with or like that? Because our formulas that will begin to appear are sure and are right if omega is certain and the empty set impossible. That means that if you roll your die, you are sure to obtain something inside omega. And this is not obvious in the real concrete world. Maybe my die could be balanced in between two sides, okay, in equilibrium. So you want that obtaining nothing is impossible. Your die will fall on one side and will show the upper side. This time you can define the contrary of the event A, that is not A, of course. And not A means here 1, 3, 5. So it's not an even result, it's an odd result. So by definition, A bar is everything but A, and in our example, get an odd number. B and C are contrary events. Yes, if you think about the situation here, if you have a closer look here, you can see that the event C is all that is not B. And in the other sense as well, of course. B is all that is not C. So B and C are contrary events. B equals C bar and B bar equals C. So that means that B and C are mutually exclusive. That's another term that has been to define here. Mutually exclusive means that two events are impossible to realize at the same time. So mutually exclusive events are not necessarily contrary events. An example here, get 4 is an event and get less than 3 is another event. Both are mutually exclusive, but they are not contrary events. Okay, the first one is not all but the second one. Now, once we define all of that, with the possibility to use the tools on sets, we can calculate probabilities on a finite set. That means on a set that contains a finite number of elements. That means non-infinite. So, an event is named by a letter A, whatever the event. It owns some outcomes among the whole set of possibilities of omega. So A is a part of omega, a subset of omega. And it contains, actually, a certain percentage of chances inside omega, between 0% and 100% of the possibilities. And this percentage can be considered, can be seen as a number that will be defined as a probability. So it's a way to define intuitively a probability of an event, but it will be enough for us. Just remember that a probability of an event is a number between no and 1, okay? Because it's between no percent and 100%. So, if we define in a proper way, so better than that, a probability, mathematically, we've got results that come directly and very quickly, and that are true in any case. Here are some kind of results and thinking about probabilities. So the probability of the empty set is 0. It means that the empty set is impossible. The probability on the other side of omega is 1. The chance to fall into omega in the end are 100%. And between them, a given event has a probability that it is obviously between no and 1. So a first formula assesses that P of A plus P of A bar equals 1. Yes, it can be considered as obvious, because if you have 30% chances that A occurs, then you have 70% chances that it doesn't. And of course, the sum is equal to 1. The formula that is in the following is actually the same formula, but we're not working here inside omega, we're working inside A. We seen earlier that A could be parted, okay, with a partition between A inter B and A inter B bar. So just have a look at the first video on sets, okay? So that means that the elements of A are the ones that are at the same time inside B, or the ones that are not inside B. And if you group both, you've got A. So the probability of A is the sum of both probabilities. So we'll see it in exercises, of course. And the third formula that still looks like formulas and cardinal numbers, its probability of A in B equals P of A plus P of B minus P of A into B. So next we will understand it in exercises. So these formulas are very useful, but they don't tell us how to calculate a probability. We've got to have another formula, but which will be true only in case of equally likely outcomes. So you have to form a sample space omega that contains equally likely outcomes, outcomes that have the same chances one to the other. If this criterion is met, so or then the probability of A can be defined as the cardinal number of A divided by the one of omega. So that are just the number of elements of A divided by the total number of possible elements. Okay, let's apply all of that in 3 exercises. So let's call back our formulas in order to see our tools. Exercise 18. A random experiment consists in taking one integer at random among the set 1, 2, 3, 4, 5 until 20. Okay, so it's very simple random experiment. First question, determine cardinal number of omega. Yeah, let's just have a look at omega, because the statement of the exercise, the text of the exercise, don't tell us about omega. We have to create it. So let's display a scheme like we did earlier in combinatorics. The experiment consists in taking one integer at random inside this initial set. So we've got the number n equals 20, and we have to pick at random p equal 1, one number. What could be a possibility? It could be 1 or 2 or and so on, or 20. So in this case, the special case, when p equals 1, omega is actually equal to the initial set. This is the same set. So things will be simple in this kind of exercise. The cardinal number of omega is 20. Now let's define events. Let's name some events. A, get at least 15, and B, get an even number. Determine P of A, P of A bar, P of B, and so on. Well, we've got tools, okay? The blue formula and the red ones. So we've got weapons. Plus, let's make a scheme in detail of omega with inside the set A, the set B, and their intersections. And let's place the 20 elements of the initial set, or omega. This is the same. So, in A into B bar, for example, you've got 15, 17, 19. Because A contains the numbers that are at least 15, okay? And B contains the even numbers. So in B, in the blue zone, here, you've got all the even numbers between 1 and 20. So outside, you've got odd numbers. And the odd numbers of A are 15, 17, 19. At the center, you've got the numbers that are at least 15 and even. So that are 16, 18, 19. On the right, you've got numbers that are not at least 15, so at maximum 14, and still even. So 2, 4, 6, 8, 10, 12, 14. And outside A union B, you've got all the numbers that are not at least 15 and not even. So all the rest is 1, 3, 5, 7, 9, 11, and 13. I didn't wrote them because of the room I've got here. But we can imagine they are here. So now, the probability of A can be given by our formula. Probability of A will be the number of elements in A divided by 20, which is the cardinal of omega. That's all. So, sorry for the commas, okay, I would have written points. No 0.3 for the probability of A. The probability of A bar, no. Well, I've got a formula to compare both probabilities, so let's use it. 1 minus 0.3 is 0.7. Or 1 minus 6 over 20 is 14 over 20. Then the probability of B. Well, inside B, you've got 10 elements, so 10 on 20, 0.5. Now, the probability of A into B. There is no formula that helps us to calculate probability of A into B. Okay, you've got relationships between this probability and others, okay? But you don't have a probability of A into B with directly the use of P of A and P of B. It's impossible in the general situation. So you just have to count the elements of A into B. There are 3 elements, and the probability is 3/20. 0.15. So you could notice that this here with these numbers, P of A into B equals P of A times P of B. Yes, indeed, 0.3 times 0.5 equals 0.15. But this is a coincidence, okay? And I did it on purpose in this exercise because I want to show this kind of coincidence in a further exercise. So let's forget about a general formula on P of A into B. Finally, P of A union B. So you can count here on the scheme the number of elements of A union B and see that there are 13 elements. So the probability of A union B is 13/20, which is 0.65. But you've got a formula for P of A union B, so you can use it instead. And of course, the result will be the right result. Okay, this was a very simple exercise because the beginning was simple, okay? So let's see some more complicated situations. Exercise 19, a random experiment consists in a simultaneous draw of 3 letters in our alphabet. So since you are drawing more than one element in an initial set, things are complicated. And you have to use combinatorics in this kind of exercise. So if you want to determine the cardinal number of omega, you have to define properly this set. You've got an initial set, our alphabet, and you have to take at random 3 letters. Plus, you've got a word that is a very important word in the exercise, simultaneous. Okay, it means that you are taking 3 letters at the same time, so you can't take twice the same letter, okay? And you don't have to use order. There is no first letter and the second one and so on. They are taken at the same time. So no order and no repetition. You are in combination. Omega is the set that contains all the possible groups of 3 different letters. And there are a lot of possibilities coming from our alphabet. To count the elements of omega, you have to use combinations. And here, C26, 3. That is 2,600. So I just wrote 3 examples among 2,600. It's a very big set. Now, we have to continue this kind of exercise with the same kind of questions as earlier, but the answers will be a little bit more complicated. We set the following events. A, get 3 consonants. B, get 2 consonants. C, 1 consonant. And D, 3 vowels. So first question, are they mutually exclusive? That means, is it possible that a group of 3 letters, like P, D, G, can belong to A and to B at the same time? Okay. Or is it impossible? If it's impossible, A and B will be named mutually exclusive. So, well, yes, it's impossible. P, D, G belongs to A because there are 3 consonants. So it doesn't belong to B because inside B you just want 2 consonants. It means 2 consonants and 1 vowel. Okay, it could be the first example, FAQ. FAQ belongs to B and not to A or C or D. PGG belongs to A and not to B or C or D, and so on. They are all mutually exclusive. Do they form a partition of omega? Well, if you want that here 4 sets form a partition of a bigger set, they have to be mutually exclusive, and they have to, when unified, to form omega without forgetting one element. Okay, they have to complete omega. Well, are there other possibilities than A, B, C, or D? So, well, there are no other possibilities. A group of 3 letters is in A or B or C or D. It can be as well. So, yes, A, B, C, and D form a partition of omega. So we've seen it in the end of the second video on combinatorics, but we are able to calculate the cardinal numbers of A, B, C, and D using combinations. Okay, and not only calculate the cardinal of omega. So calculate the cardinal numbers and then their probabilities. So let's make a scheme thanks to a table here that will be more clearly seen than this kind of scheme. Okay, so this is the same purpose but organized in a table. Your alphabet contains 20 consonants and 6 vowels. The total number is 26, our n. Inside the subset A, you want group of 3 letters that contain 3 consonants and no vowel. Inside B, you want 2 consonants and 1 vowel. Inside C, 1 and 2. And inside D, no and 3 vowels. So I explained you that this time you can calculate separately combinations for consonants and for vowels. And in the end, you are allowed to multiply both combinations. So for example, if you want the cardinal number of A, you have to calculate C23 times C6 no. That means that you want to calculate the number of ways to choose 3 consonants among 20, multiplied by the number of ways to choose no vowel among 6. For B, C22 represents the number of ways to choose 2 consonants among 20 and 1 vowel among 6, and so on. And you can check that the total number equals 2,600. Well, I made a mistake in my writing here. This is not 1,040. This is 1,140 for A and for B. And yes, the total number is 2,600. So I guess I corrected that in the calculation of probabilities. Yes, I used the right numbers here. Okay, so the probability of A, thanks to the blue formula, of course, is the division by 2,600 each time, okay, for A, B, C, D. So in percentage, 43.85%, the same for B, 11.54% for C, and 0.7692% for D. Okay, and D is a rare event. Of course, vowels are not in majority in the alphabet, so the chance to pick at random 3 vowels when taking 3 letters at random in the alphabet are very low, less than 1%. So of course, the sum of the percentages are 100%, and I asked to write the result with 4 significant figures. That doesn't mean 4 decimals, okay? That means 4 figures in total. So 43.2 decimals, 11.2 decimal, 0.4 decimals. I want 4 figures of precision. okay, in my number, in my result. So a last exercise, yes, exercise 20, random experiment, roll 2 dice and add both results. What are the different possible sums? So if you roll 2 dice and add both results, the lowest sum is 2 with a double 1 with your dice, and the highest sum is 12 with a double 6. Sorry, between 2 and 12 you can reach every integer. Okay, for example, you can have a total of 9 with a 5 and a 4. So the set of the different possible sums is 2, 3, 4, 5, and so on until 12. Next question, are they equally likely? So, is it a sample space of equally likely outcomes? It's proven that not. They are not equally likely, and I have to explain it to you with details. You want to roll 2 dice and add both results. So let's have an overview of all the possibilities. Each of the dice makes 6 possible outcomes. 1, 2, 3, 4, 5, 6. So let's cross the results that are possible for the first die and the results that are possible for the second one. And then I'm going to add both results in each crossing. Okay, so a total of 12 is obtained with a double 6. A total of 5 can be obtained with 4, 1, or 3, 2, or 2, 3, or 1, 5, or 1, 4, sorry. So you've got 4 different ways to obtain a total of 5, but you've got only one way to obtain a total of 12. Well, the fact is that if you die, each one, okay, contains equally likely sides. So if each side have 1 chance over 6 to be obtained, so every of the 36 couple here has 1 chance over 36 to be obtained. So if you roll 2 dice, you've got 1 chance over 36 to make, for example, a double 4 and to be here as a total. You've got 1 chance over 36 to make a 3, 1. But you've got 1 chance over 36 to make a 1, 3 as well. Okay, so each of these results have the same chance as its neighbors. Okay, and then you can see that you've got 4 times more chances to obtain a 5 than to obtain 12. So the list 2, 3, 4, 5, 6, 7, and so on is not a list of equally likely outcomes. That means that we're not allowed to use this formula inside this set. So it's a big problem for us in order to go on the exercise. So, third question, build a sample space of equally likely outcomes. Well, we just said that the pairs of results are equally likely. Each one has a chance of 1 over 36. So let's create omega as the set of the possible pairs. And then the event obtain a total of 5 will contain a certain number of outcomes inside omega. So we can see here on the right the outcomes 4, 1, 3, 2, 2, 3, and 1, 4. Okay, it's a subset of omega. So we set the following events. A, the sum equals 10. So we're interested here in the sum 10. And B, the sum is at least 10. So we want to be in this area of this table. 10, 11, or 12 for the even B. Determine P of A bar, P of B. So P of A contains 3 pairs inside omega. The 6, 4, the double 5, and the 4, 6. So the probability of A is 3 divided by 36. That's all. The probability of A bar can be obtained quickly with this formula, of course. So 1 minus 3 over 36. So that is 33 over 36. So 11 chances out of 12. And the probability of B is obviously 6 over 36 because there are 6 elements inside B. Okay, thank you for having followed this video until the end. And we will have correction session of exercises on this purpose, but in French, okay, at least for the beginning. Just next week. Thank you all, and bye-bye. See you next time.